What's up, folks? Today we're going to talk about reasoning models like O1, DeepSeek R1, Claude 3.7 plus extended thinking, etc. How to use them, when to use them. We're going to start by defining them, comparing to traditional LLMs like the regular ChatGPT interface or Claude, and then why one would use them, when to use them, how to use them, limitations so you don't go around talking about AGI, choosing between the different options that are out there, and some hands-on on the interfaces. And also I want to write a little bit of code with sample API calls for the different models that are out there. So folks, what's a reasoning LLM? Now, with traditional LLMs, when you send an input to the model, they follow a fixed number of steps to produce an output. With a reasoning LLM, when you send an input to the model breaks that down into a bunch of sub-problems before actually solving and returning a response, right? They're built for breaking down complex tasks into subparts and then solving those subparts to get to the final output. Now, how do they do that? Well, even though the implementation changes for different models, the core idea is that these models generate reasoning steps before solving any problem. So we're going to be able to visualize, when we get the output from the model, we're going to be able to visualize not only the final output for what we asked for, but also we're going to be able to validate and verify the reasoning behind the generation of that output so that we can see if it's coherent, so we can see if the way the model is tackling the problem makes sense, and so on and so forth. So you can already see that these models are built for situations where we have complex problems that we need a lot of thinking and deep problem solving to be able to solve. So to demonstrate an example, I'm going to open up Claude over here, and I'm going to click on the Claude 3.7 Sonnet model, but I'm going to activate extended, which will make this model activate its reasoning capabilities. Well, the actual way that this is implemented in the background, I'm not 100% sure, but the idea here is that this is actually just calling a different model than the traditional Claude 3.7 Sonnet that has extended thinking capabilities. At least as far as I know, that's how it's implemented in the backend. So if I put a little prompt here, like plan out a to-do list app in JavaScript, and I send that out to the model, what we're going to be able to see that's very interesting is the reasoning behind the execution of this task. So as you can see here, the model is thinking, it's analyzing, etc. So if I open this up, I'm going to be able to see under this little page here, which is not the output that we get, but actually what's behind the output is the reasoning that the model went through in order to generate the response. So the model is saying the user has set a preference for me to always be the most efficient and instructive, blah, 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 blah. This is clear behavioral preference that I should apply. The user wants me to plan out a to-do list app. Since the user wants efficiency and unnecessary information, I should be concise, focus, avoid unnecessary explanations, organize the plan should include core features, component structure, data model, key functions, implementation steps, So these are the reasoning steps that the model generated before it actually generated the output that I asked for. And this is the kind of stuff that reasoning models are capable of. And you can get similar things like this with Gemini or DeepSeek R1 and so on and so forth. All right. So going back to this, the point is to say, okay, a model can generate reasoning steps before generating an output. They are, optimal for solving complex tasks. Great, but I mean, how is that possible? What is different about the way these models are trained versus the regular LLM that we're used to, like a traditional, the GPT-4o model from OpenAI, the ChatGPT that we all know and love, or some open source LLM that comes out. Whatever model that comes out, even though there's a lot of variability in the way these implementations are done, but the core idea is actually well summarized in this really cool paper by Meta called Llama 2. This is the paper behind Llama 2, which you can check out right here. If I go Llama 2 paper PDF, it's called Llama 2 Open Foundation and Fine-Tuned Chat Models, right? And they have this very nice diagram on showing the basics of how to train an LLM, right? So all of these models usually go through the following process. You pre-train them. You pre-train these models on a large corpus of text. For example, Llama 3.1, the Llama 3 series models were trained on like 15 trillion tokens of text data, which is like the full internet. It's a bunch of text. It's crazy. right? And that pre-training phase generates a base model, which is a model that somehow can take in some text and output some text. And that's it. That's what the model can do. In order to make this model safe, in order to make this model helpful to other people, which is not something that's necessarily embedded in the internet data, we need to go through a second phase, which is what is called reinforcement learning with human feedback, which essentially means that you're going to fine-tune the model to be helpful and to be safe. And the way that you do that is by having some chat interaction where users will send in requests to this model, and then we're going to generate a few options. And then these options are going to be selected by human feedback, where people are going to say, okay, I like this response, I don't like that response, right? And these responses from human annotators are going to be used to create this safety reward model and this helpful reward model. Essentially, you're going to create reward models that can guide a fine-tuning process that uses some fancy algorithms that we're not going to talk about, because I would say a lot of stuff that I don't really know how it works deeply. But you're going to fine-tune them with rejection sampling, proximal policy optimization, a bunch of techniques that will essentially make the base model align more with the reward signal associated with being helpful and associated with being safe, right? So by doing that in a loop for a gazillion iterations, you get to a model that is helpful and hopefully won't say stuff that it shouldn't. And that's a basic way that you train an LLM today. Now, what is cool about reasoning LLM is that the core idea, even though there's a bunch of architecture implementation stuff that requires a little bit of expertise to go really deep into it, the core idea is that the reasoning LLM introduces essentially a phase of fine-tuning the space model on thousands and thousands of chain of thought examples. And if you don't know what chain of thought is, to understand what this means, I'm going to open up the paper, chain of thought paper PDF. And if we go here on this paper and we take a look, it's essentially a prompting technique that teaches the model how to think by showing it examples on reasoning over some problem. Okay, so for example, in the first time this paper came out, they showed an example with the standard prompting versus what would be the chain of thought prompting. And essentially, that was a question that requires some very simple math reasoning, and there was the answer, right? So this is an example of a few shot prompt where you show the model one or more examples of how to solve a certain type of task, and then you ask it a question on the same category or topic, but you don't, you show it a bunch of examples, but you don't show anything more than just this is the question and this is the answer. Now, with chain of thought prompting, you show the question, but when you show the answer, you also show the process to get to the answer. So for example, Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So Roger started with 5, 2 cans of 3 tennis balls. Each is 6 tennis balls total. So 5 plus 6 is equal to 11. So this is the reasoning steps to get to this answer. And by prompting the model with examples on how to think, you get the correct answer. You improve performance quite a bit. And they even show that if you only induced reasoning by telling the model to think step by step, that would increase performance, I think, by 34%. Let's check that out. Yeah. No, not 34%. Perform the rest. 34% of the examples contain in addition to no. Just let's think step by step. Step by step. All right, I don't know where the step-by-step bit is, but it's here somewhere. Let me see. Okay, I'm regretting that I went to the step-by-step issue now. Okay, showing a bunch of other examples. All right, doesn't matter. What they did with reasoning LLMs is, let's not fine-tune the models on just internet data. Let's fine-tune the models on thousands and thousands of examples that contain the reasoning process to get to the corresponding answer. And we know this information, not because of the closed source LLMs that we know and use all the time, but we know that because there's a really awesome paper from DeepSeek R1, which is a paper that I definitely advise you to take a look. It's called DeepSeek R1, Incentivizing Reasoning Capability in LLMs via Reinforcement Learning. And what's cool about this paper is that they show they show a bunch of fascinating things. A lot of them, it goes a little bit beyond my head in order to explain it. But there's two cool things here. This DeepSeek R1 0 model, which is the less performing of the models, was actually performing in par with today's like top-notch models without going through a supervised fine-tuning phase, which is what usually happens with your traditional process for training an LLM. You see, you go through this supervised fine-tuning phase. This model didn't go through that, and nevertheless, they achieved, only with reinforcement learning, a lot of success. However, in order to get the super-duper good, amazing DeepSeek R1 model that everyone knows and loves, they did this on fine-tuning on thousands of examples with chain of thought. So fine-tuning, let me see, chain of thought. Why am I not accessing this? Yeah, we can see here in the DeepSeek R1 paper, they talk about curating reasoning prompts and generating reasoning trajectories by performing rejection sampling from the checkpoint from the above RL training. The point is, there were essentially two models that came out of this paper. R10 that was trained without this fine-tuning phase on chain of thought examples, and one that actually did start from a model that was fine-tuned on thousands of examples that show reasoning examples, which led to this boom of popularity because it's an amazing model. It's open source, and if we go to artificialanalysis.ai and we take a look at their artificial analysis intelligence index, you see here that DeepSeek R1 is top-notch, competing with O3 Mini High and O1 from OpenAI, and it's a really powerful model. Another one that's really capable is KWQ 32 billion parameters, which is right below DeepSeek R1. The difference is that this model is much smaller. So for example, if I open up my terminal, and I can show you folks that if I delete this and I make it big and I just go to a different folder, I can say Olama run QWQ. And this is running that Qwen 2.5 32 billion parameter model, I hope. And if I say, hi, tell me a complex joke, the model is going to open up a thinking XML tag here at the top that you're going to see in just a sec, hopefully. Come on, show it to me. There you go. So this is the model thinking before it sends the output. So you can see here, think. So the model is going to think deeply about my very complicated input, which is tell me a complex joke, before the model sends me a response. So, which is amazing because, I mean, this is a model that compares with the top-notch models out there, but it's a model that I can run for free locally on my machine. So something to think about, and it's pretty cool. Now, going back to our little presentation, now we know that despite, we're not going to go into mixture of experts, the specifics of the implementation techniques used for these models, because there's a lot of variability. There's talk about how other models were trained and the differences. Like, for example, there's some information in the internet about how O3 uses this program synthesis approach that kind of reshuffles algorithms and patterns to generate responses and some stuff that's a little bit beyond our scope right now. The point is, these are models that can output reasoning steps for solving a problem, and we can leverage that on different tasks and different problems, different contexts, and so on. So, in essence, reasoning LLM is a model that's designed for complex multi-step problems. It generates intermediate reasoning steps or thought process before sending a final output to the user. It breaks down these tasks into these logical sub-steps, which is something that's very similar to human step-by-step problem solving, in a way, I guess. And they will generate more accurate and explainable results on challenging tasks like math problems, logic puzzles, and code debugging, something you can investigate by going to the artificialanalysis.ai website and looking at the indexes of the metrics they use, the benchmarks they use to assess the capabilities of these models, like MMLU Pro or GPQA Diamond. GPQA Diamond is just 448 questions at a graduate level for different fields. Live Code Bench, SciCode, IME, which is a math It's a math benchmark. So benchmarks that assess different capabilities related to intelligence, and you see that these models do very well there. The point that I will make now is, okay, so let's understand a little bit more in depth how they differ from traditional LLMs. And I think there are a few points that are interesting. Traditional LLM has this direct pattern-based prediction, which is the thing I said in the beginning. It's a fixed number of steps to generate an output, which just means that in some random neural network, you have a certain set of forward passes from when you get the input to get to the output. And with a traditional LLM, that's going to be fixed, while with a reasoning LLM, that's not going to be fixed because they're going to generate these reasoning steps, and the process to do that makes the number of forward passes a little bit more variable. Now, they're going to be these one-shot, I'm feeling lucky approach, which is just to give you an output. They're not going to say, look, I'm getting generate, unless you ask for it. They're not going to say, look, I'm saying this because of all of these step-by-step procedures that I went through, etc. They're just going to tell you their truth of what the output should be. They're quick, but they're less reliable on complex tasks, because on complex tasks, you usually need to validate what's going on and understand why decisions are being made and why tasks are being solved the way they are. And they don't have that. They have no explicit reasoning steps. While reasoning LLMs will have step-by-step problem solving. They will fine-tune with chain of thought examples usually. So they'll have this chain of thought approach to solving the problem, which is generating these intermediate steps before sending the output to the user. They're going to be more methodical, but they're going to be slower. So you're going to have to consider latency as one of the components of the problem when using these models. They're going to show the intermediate steps like I showed in Claude a while ago. And that's pretty much it. Now, with all of that being said, the key capabilities of reasoning LLMs are, well, first and foremost, chain of thought reasoning. So this internal dialogue approach that applies step-by-step problem solving, and this idea of thinking out loud through text, just like the Quen model did here, where the model kind of did some overthinking on the joke I asked for. And yes, seems to be a bit both. All right, I'll go with that version. It might be better. I don't even know. Okay, let's see. I think this is the joke. Why did Schrodinger's cat get expelled? Because during exams, it was found in a quantum superposition between cheating and not cheating committee couldn't resolve this thing. All right, that's pretty cool. That's nice. All right, so now going back, the second thing that's a key capability of these models is something called self-consistency. Now, these models tend to be very good at verifying their own answers, which makes them very nice for judging outputs of other models and validating the reasoning over why they're judging the output of another model the way they are. They have the ability of revisiting problematic solutions because they can backtrack their thinking, which is really cool. And they usually, they have this ability to organize their reasoning steps, and they're very good for structured outputs. So if you want to use a model to generate some JSON with organized keys and specific values instead of getting some chat conversation response, they tend to be good for that kind of stuff. And they numbered out their reasoning steps so you can trace back and see, each one, so you can validate with the actual output that was generated. That's pretty cool. Now, you can ask why one would use a reasoning LLM. And this is a very interesting point made by the artificial analysis folks. They put out a report every quarter of the year on what's going on in AI. And their 2024, the fourth quarter report of 2024, they had this graph that I really like on the demand for models being concentrated on release from top AI labs. And the things that matter are model reasoning quality and price. So what people tend to care about the most when they're going to use a model? Well, people care about reasoning quality, and they care about price. So because reasoning quality, as you can see here on the this little heat map on the right, is it's the most voted thing, the most important criteria for choosing a model, because people want the best model all the time, right? That kind of justifies itself why one would care about such indexes like this artificial analysis intelligence index, because people want to use the absolute best stuff right now, right? I think that the point that we're making here, folks, is that imagine that a small model came out that is really good. It's kind of good. Like, for example, a lot of people kind of dismiss cool models like Llama 3.18b or Mistral R, whatever it is, because they're not the best model. But the point is that these models have other features that makes them interesting. Like they're much faster to run. You can employ some very fancy, interesting approaches to get the best performance out of them by leveraging prompting techniques or maybe fine-tuning, etc. However, in general, in industry, people care about what's the smartest model out there, so it can help me make a decision or whatever the case may be. So, but there's a bunch of other stuff that goes into play. For example, the second place was price. Obviously, you want the best model for the cheapest price possible. You also care about things like embedded knowledge, which is all the context the model has access to in order to respond to the user. So, for example, we usually connect models today with web search using tool calling or like the new MCP servers that are coming out. People care about context window. Like, for example, you can get 128,000 tokens of context window with ChatGPT. You can get 200,000 with Claude, and you can get, I think it's let's see, Gemini context window. I think it's like 2 million, 1 million. It's like a huge number. Gemini 2.0 context window size. It's a 1 million token context window, which is huge. I mean, this is like thousands of pages of a PDF. I haven't fully explored this, but it's pretty impressive. Now, there's a bunch of other stuff, but I guess the final 2 points that I would say is that people care about latency, so how fast you get a response. And there's different things that you can think about. So there's throughput, so how much you can get out of that model per time. And latency, which is just how long does it take to get a response from the model when you send it, right? So and you can look at it from different perspectives, but the whole point is how good the model is, how cheap it is, does it use the right context, does it have access to the right embedded knowledge, how much text I can send inside the model, how fast is it, and that's pretty much it. Obviously, there are other factors like, is the model open source for privacy issues? Can the model do function calling, which means connecting that model to some external capability like sending emails, searching the web, etc. And can the model have a JSON mode, which allows it to have structured outputs, which is very useful for extracting from structured information from PDFs or websites, etc. And the top models, as you can guess, at the end of last year, I haven't checked the latest numbers, but at the end of last year, OpenAI was heading with 83%. Meta was in second place because it has a bunch of amazing, powerful open source models that have similar capabilities to the closed source versions, but they're free in the sense that their models are open source, so you can download the weights and use it for whatever you need, but you have to have the infrastructure to run, for example, the more powerful models like Llama 3.1, Llama 3.2. I, with Ollama, have on my terminal here, I can run Ollama, run Llama 3.1 or Llama 3.2 or Llama 3.3, which is kind of big, so it takes a little bit. But if I run Llama 3.2, which is like 3 billion parameter, it's very fast. So I can say, hi, tell me a joke and explain why you did it. And the model is just going to go super fast. It's going to tell me the joke. I choose a joke for, okay, so why couldn't the bicycle stand up by itself? Because it was too tired. Like, that's pretty good. That's pretty good. All right. So that's why you would use a reasoning model, because what matters in terms of decision criteria for picking LLMs today, at number one is reasoning quality. So if you have a model that's specialized in being able to solve complex problems, that's the model you're going to want to use, and you're going to want to use it for the cheapest price possible. You're going to want the fastest version of that. For all of those points of information, if you want to make a decision for yourself, what I advise you to do is go to artificialanalysis.ai, and you can look at intelligence, speed, and price, which, as you can see, I love this website because they already organize the information associated with people tend to care about the most. And you can see that the fastest model right now is Gemini 2.0 Flash, with 254 output tokens per second, which is like how much text they can put out per second. And you can see that the slowest model right now is GPT 4.5, even though GPT 4.5 is like the absolute most insanely priced at $93.8 per 1 million tokens generated. And then you have a bunch of cool in-between options like Llama 3.3 at 125 output tokens per second, and so on and so forth. And you can check out and see which one you want to use. Now, for example, one interesting option, just looking at it from this perspective here, would be to use either Gemini 2.0 Flash, because we know Gemini 2.0 Flash scores high here on intelligence, but is also very fast. So maybe that's something that matters to you. Or you just want to use like the top-notch model possible, but you don't want a model that's like below a certain threshold of speed. So you can look at DeepSeek R1, which is like the second best right now, but it's also top-notch in terms of speed, even though it's like the slowest of this like group of models here. It's still pretty fast for a reasoning model, so you can check that out. All right, so with all of that being said, folks, we can move on. So hopefully I find where my slides are. There you go. No, that's not my slides. Where are my slides? Okay, so I just lost my slides, folks. Don't be alarmed. And I have no idea where my slides are. Okay. I have no idea what's going on. There you go, folks. Here we are. When should you use a reasoning LLM? Now, you should use a reasoning LLM when you have background tasks where latency is not super critical, but they are of like somewhat high importance. So you really need a high quality result for that. You have complex problems, right? Like they require deeper thinking, and you have tasks that benefit from extensive reasoning. So for example, if you have a complex coding project that you need to do, or you're a math student and you're not being able to solve some very tough integral, whatever the case may be. And one of the biggest things that I use these models every single day for is research and planning heavy workflows, because sometimes I feel like perhaps I'm not being extremely effective on the way that I'm approaching a project, especially when projects are like very big and they require months length of planning. So reasoning models for this type of use case are absolutely amazing, especially when you combine them with the right context information, which you can obtain by using tools like deep research from ChatGPT, or deep research from Perplexity, or an MCP server that does web research with Claude Desktop, whatever the case is, or Gemini. They're very good for research and planning heavy workflows. So ideal use cases for these models are complex problem solving. So math, logic, multi-step reasoning stuff, deep analysis of multiple research papers, analyzing large documents, interpreting meeting notes for these meetings that go on for like an hour. So you get the full transcript of that meeting, and then you put it into a model, and then you ask for whatever you need from those transcripts. Planning an agency, like for example, workflow planning. I do this all the time. I do research and workflow planning all the time with O1, or with extended thinking in Claude, or with DeepSeek R1. Agentic systems, they're very good at essentially powering an agentic system, which is a system that's embeds like an LLM with a bunch of functionality in some sort of loop to solve a task. And strategic decision making, when you really need to take a step away from some situation to decide on something, use a reasoning LLM for that. And in terms of practical applications, you can start thinking about using these models as data analysis, for example, medical diagnosis, even though obviously I'm not saying go out there and do medical diagnosis with a reasoning LLM. There's a lot of evidence right now coming out that they can be helpful as a collaborator with a doctor to perform better medical diagnosis, interpreting complex information, anomaly detection, background processing, which is something I haven't used as much, but I definitely want to try out a little bit of batch processing workflows when you have like a bunch of stuff you need to do to a bunch of documents. And this is like a very interesting one that I actually found out, folks, on a very cool article that I want to share with you, which is it's from Latent Space. If you don't know Latent Space, folks, what are you doing? You just follow them on their Substack. They put out like super high quality AI engineering content. And they have this article, O1 isn't a chat model, and that's the point, how Ben Highlight turned from a O1 Pro skeptic to a fan by overcoming his skill issue. The point is, they make a really interesting comment here in this article, folks. I think it's point number 5, about the capability of these models for evaluation, which is right down here. There you go, bonus evals. I have historically been skeptical about using LLM as a judge. Folks, if you don't know what LLM as a judge is, it means that sometimes when you want to evaluate the output of a model, doing it manually is very annoying. So people started using LLMs to evaluate the correctness of an output by feeding that LLM with the original objective goal context and then the output answer that was generated by another LLM potentially. And then the LLM as a judge is just going to take a look at those and say, okay, this is correct, this is not correct, and so on and so forth. And I was also very skeptic, and I was very happy to read this article. Fundamentally, judge model suffers from the same failure modes as when generating the outputs in the first place, which means, how you're going to trust the LLM to be a judge when the LLM itself is a probabilistic model that sends an output that's not deterministic, right? But O1 shows a ton of promise. It's often able to determine if a generation is correct or not with a very little context. And the reason for that is because they can somewhat backtrack and they can evaluate their own thinking, which is a really cool thing to do because it makes them better and more trustworthy judges of the correctness of anything. So that's kind of the point behind this idea. So evaluation tasks are like a good use case for reasoning LLMs. So quality assessment, verifying workflows, LLM as a judge, etc., etc. Now, folks, I've said all this amazing stuff about reasoning LLMs. Now I want to talk about how to use them. So how do you use a reasoning LLM? And I'm going to use a whiteboard for that because we have there's a bunch of cool stuff that I want to integrate into this conversation. So I want to go to ScaliDraw, to my little ScaliDraw. I have a little drawing here, course thinking models. So here, this is where I'm organizing all this information. And I'm going to go over to how to prompt reasoning LLMs. And there's a bunch of stuff to say, folks. Again, this, I think for this one, most of the information I took from this article, folks. Let me just put up this article again. O1 is a chat model, that's the point. So check out this article by Ben Heilich and Swix and Alessio, and check out the latent space. I think they have a YouTube channel, they have a podcast, and they have the Substack, and I follow them everywhere. They have amazing stuff. Now, how to prompt reasoning LLMs? Well, there's a bunch of stuff out there. The core idea is that you're not going to treat a reasoning LLM like a chat model. What does that mean? It means that you're not going to follow the traditional, which is here on the right. You're not going to follow this process, which is you're going to open up some dialogue with ChatGPT. You're going to have some context initially, some question you want to ask, and then you're going to get a response. And then you're going to say, oh, no, but what about this? And then you're going to get a response. You have to plan for an actual reasoning LLM. And what does that mean? It means that you're going to be super thorough at the beginning. So the model can go through the process, you leave the model to solve the thing and then give you a response. So that's how you're going to think about prompting a reasoning LLM. So what does that mean in practice? It means this. Let's organize it as you're going to set the goal. Okay. You're going to set how you want the response to look. So the return format, whatever warning, safety, whatever thing do you want to say, like, look, whatever you want to filter out, you say third. So be careful to make sure that the name of the trail is correct, that it actually exists, blah, blah, blah. And then you're going to do the context dump, which is if it's a PDF, if it's your, the materials for some exam you need to study, whatever it is, it's at the end. Now, when I say at the end here, folks, this is a very interesting point. Ben Heilich, which is also the co-author of the article, that amazing article that I just showed, and it's actually the source for this slide. Ben Heilich put up a tweet that's very important to make the distinction. If you're working with Claude Desktop plus extended thinking, the context should go before the request, all right? And there's reason for that. I think it's related to if you ask the model something at the top and then you put a bunch of context, the model might quote unquote forget. It might get missed on all that context information. Whatever the case is, put the context before if you're using Claude Desktop plus extended thinking, and put the context after if you're using an OpenAI model. That's according to the OpenAI docs and to the OpenAI best practices that you can check out in the OpenAI platform documentation. Okay, so a set of bullet points to emphasize all this information and give you some extra tips. Don't think about prompts when you're using a reasoning model. Think about briefs. And the brief is going to be a combination of goal, return format, So it's going to be Go. Let me just make this red. So it's going to be a combination of Go, return format, warnings, which is like with the stuff you want to filter, the stuff you want to avoid, and then the context dump, which is going to be your document, your context knowledge, your website text, whatever it is. So think about it in terms of briefs, and this is the structure for a brief. Now, the second point is I like also using reasoning LLMs as report generators. So I actually have a folder here on my machine. If I open up this LLM research reports, so I generate these reports about different topics that I'm interested in, like human attention or statistics or methods for studying user interfaces, whatever it is. And I generate these with an agentic approach that's backed by a reasoning LLM. So thinking about them as report generators is a very nice approach. The third thing is put as much context as you can into O1. I mean, really use that context window of 128,000 context length if you're using O1. But for whatever reasoning LLM, put everything the model needs to know in a super organized fashion as much as possible. So for managing context properly, you can look at projects like Git ingest. For example, if I go to this DeepSeek R1 repo, right? And I open up the GitHub link and I go gitingest.com and I do this, I get this really cool one single prompt containing all that information. And I even get the information on how many tokens in that prompt, everything that's in there. So this is awesome because this allows me to just copy this and I can send this to some LLM to get some response. And I can do that with any GitHub repo and it's free and it's amazing, right? Another thing that you can do is, for example, if I go to the OpenAI, the LangGraph documentation page, right? And I click over here. I'm in the LangGraph documentation page. This is not the LangGraph documentation page, but let's go. There you go. If I go to this website, right? And I open up the link here and I write r.gina.ai, what's going to happen is that this page is going to turn into a magic markdown file that I can directly put inside a large language model to get answers from. So this is going to be structured in the way that's optimal for a large language model to consume and produce responses and so on. All right. So this is pretty awesome. All right, folks. And there's a bunch of different ways and different tools you can use to properly leverage these LLMs. But this is like a couple of tips that I would give you to, get you in the loop. All right. So definitely do that. So put as much context as you can, as I'm saying here, and use the right tools for managing this context. So things like Git ingest or r.gina.ai for websites. Let me just put this like here. And there's a bunch of other stuff like the PDFs and the documents, and there's different tools that are good for parsing these PDFs. But the point is put as much context as you can into O1, right? Now, the problem with these models is because it's not a simple prompt that we can write, but it's actually this brief with all these with all the structure. It's kind of annoying to do that ourselves, let's say, with just writing for like a long time, like this overcomplicated prompt to a model. So what you can do is you can use tools to transcribe your audio so you can dictate easily to the model. And the problem is whatever dictation tool you have on your computer, be it a Windows, Mac, Linux, whatever it is, it's probably not going to be the absolute best. And the one that I use and recommend a lot because it's amazing, it's called Super Whisper. So I'm going to try to use it now and hopefully it will not screw up my audio for this video. As I'm going to open up, let's say, ChatGPT over here. I'm going to select O1 and I'm going to talk for a minute. Hey, how's it going? I am teaching about how to use reasoning LLMs effectively, and I want to show my students the good stuff about how to properly use these models. So I was wondering if you could draft a very nice report about this topic that allows them to understand what's the difference between a reasoning large language model and a traditional LLM, but make it intuitive, and that's it. So folks, what's going to happen is that I was just able to easily create that prompt with audio without having to actually write down everything, which is super, super helpful to actually be able to be fast and effective with these models. All right? So use not necessarily just Super Whisper. There's also Careless Whisper. There's a bunch of tools. Use some sort of audio transcription and then talk for a minute or two and then send that as an output, as an input to the model. All right. Finally, folks, develop good criteria for what is good versus bad. This is, I think, one of the best tips from this article. That is the same article I just mentioned, which is Swick's pro tip. Developing really good criteria for what you consider to be good versus bad helps you give a model a way to evaluate its own output and self-improve, fix mistakes. You're moving the LLM as a judge into the prompt and letting O1 run it whenever needed. So because these models generate reasoning steps and they have this self-reflective nature, one really useful thing that you can do is actually learn to define good criteria so that you can embed this into the brief prompt that you're sending to these reasoning LLMs to get a much better performance out of that model, because the model can incorporate that and kind of have like for free this LLM as a judge internal model that will apply to get you the best output possible. And this is a really cool tip because usually we have these, it's very hard to evaluate large language models and agents and so on and so forth. And I think that part of the problem is because we don't have a criteria internally of what is good and what am I looking for this particular thing, for this particular task. A lot of the things we want these models to do, we don't have like a clear, concrete criteria for what we're expecting to get. And this is probably one of the most important things. So a way to get to that is, for example, to brainstorm a little bit with a model. It doesn't have to be a reasoning model for that. You just brainstorm a little bit with the advanced mode in ChatGPT or whatever the case may be. And you trying to figure out, okay, what is the real criteria for what I'm looking for? And when you get to that, put that as text into the brief prompt that you send to these models to get the best performance possible. All right. And I think they show an example here. Have it writing something, write a thing yourself, have it critique the diff, stick the crit, I try pausing negative, but I find the diff critique sufficient. Yeah. So in this example, the user is actually sending to the LLM the criteria for what's good. So it's sending these 4 points plus I find the diff critique sufficient. So it's kind of like concretely saying what the criteria is so the model can get the best performance possible. All right. So that would be the last thing I would say. And that's how you prompt properly a reasoning LLM. And obviously after I cover this more theoretical presentation, I'm either going to do this video or the next one, which is just going to be hands-on with these models and trying out different things. But this video is going out on 50 minutes, so maybe I'll do a second YouTube video on this topic. And moving on, let me just see here where we were. There we go. Here we are. So in summary, don't treat prompts to these models don't treat this model as a chat model, like we were talking here on the right. Treat it as a non-chat model. So write briefs. They're composed of a goal, the return format, the warnings, things you want to filter out, etc., and then a context dump with all the information the model should know to give you the best response possible. Use them as report generators to get you these summarized reports that compile a lot of information in a neat, structured report. Put as much context as you possibly can into O1, leveraging tools like Git ingest or r.gina.ai or llm.text, and just put PDFs in there, put all the stuff that it might fit into the context window of the model so that the model has all the information to get you the best response. When you're writing this brief prompt to the model, if it's too much that you need to write down, maybe use an audio transcription tool like Super Whisper, so that it automatically transcribes your audio so you don't have to type it all down because it can be a little bit slow. And learn to develop good criteria for what is good versus bad with these models. And remember, if you're using Claude Desktop plus Extended Thinking, Claude plus Extended Thinking, the context goes before, but if you're using OpenAI, the context goes afterwards. All right. And folks, kind of to wrap things up, there's more theoretical presentation here. There's a bunch of limitations to these models, but there's like a few points I want to make with what's what we need to consider when using these LLMs, especially if you want to deploy them somewhere or do something more fancy with them, is increased latency is the first one, right? Extended thinking means they're going to think for a while, so they're going to take a few seconds when a regular model would take like a second, right? So it leads to longer response times. It will always lead to longer response times, so you need to be aware of that if you want to use the model. They're going to use more resources, and that's if you're using an open source model, you need to know that that's going to take more computational resources. So if you have like some machine that you deployed, you need to know that. Because they generate all these reasoning steps to generate some output, etc., they're going to cost more. So if you're paying for whatever model it is, they're going to naturally be models that are going to be more verbose. They're going to cost more tokens to generate text, and they're going to, take longer for processing the text that you sent. So that should be taken into account. I put scalability challenges here, folks, but the point here is that because they take more time, because they take more tokens, you have to make some performance cost latency trade-off assessment to make sure that you can scale in proportion to the resources you have access to, computational power, etc. Because, you have models that take a while to respond, that cost more, they're more verbose, etc. So don't use them for everything because you're going to face those scalability challenges. Now, when it comes to reasoning quality, you're going to see that these models have some reasoning quality limitations. I think that the best way I saw this put is again on this awesome article by Latent Space, by Ben Heilich, Swix, and Alessio. And they make a couple of points on when you should not use reasoning LLMs. So what O1 doesn't do well? Writing specific voices and style, that's very niche, and the model doesn't do that very well necessarily. Think about it, right? All the people that they're kind of overthinkers, they're probably not very good at, mimicking styles of other people talking, etc. I guess this is kind of like an inherent quality to thinking too much. And building an entire app. This is kind of true always, right, folks? If you want to build a full stack app with a bunch of bells and whistles and features, if you want the model to just generate the whole thing, you're going to face problems. They're very good at, for example, generating full Python scripts because Python scripts are much simpler to make. But for building full-fledged entire apps, break down the problem a little bit more. Don't go for the O1 model right off the bat because they're not going to be great at that. But not only that, there's a bunch of other factors that I think are interesting to consider. For example, they're going to have varying performance across different subject areas. So you're going to see that they do very well in this one thing, but they might not do very well in, for example, historical analysis or something like that, but they're going to do well in these coding math challenges. Remember, there's a very specific definition of intelligence in that index that we were talking about in the beginning of the video, which is related to all the benchmarks that were tested against which these models were tested on. And they relate usually to general problem solving, STEM qualities, math, coding, etc. So just go subject by subject and be careful there. They might struggle with problems that they're not during training, but if you don't know which problems were inside of the training of these models, you're not going to be able to make the distinction. And this is kind of in essence, when you know you're working on a problem for which there's not a lot of available information online that describes the nature and the characteristics of this problem, you might need to find a way to feed context properly into this model and not just, tell it, look, I need to solve this thing that no one has ever heard of and there's nothing on it on the internet, solve it for me. It's not going to work very well. And this is kind of a weird one that I've encountered working with these models, which is they have inconsistent depth of reasoning. So sometimes you might ask a model to, write me a very fancy joke, and the model will think for hours, but you solve me this quantum mechanics equation of whatever it is, and the models might be, oh yes, sure, just do this. So be aware of and always validate if the reasoning steps are coherent with the output that's generated, because they might have some inconsistent depth in their reasoning, especially when you compare it across models. So that's something to take into consideration when you're comparing different models like DeepSeek R1 or O1, the O series models, or Claude 3.7 started with extended thinking, or Gemini 2.0. Like, take a look at the coherence between the generated intermediate steps and reasoning steps they create and the output they generate, and make sure that you go for the model that has the more consistent depth of reasoning given the problem that's given and the output that's generated. And all of these models have the issue of sometimes being too confident in wrong and flawed reasoning. So develop that criteria to spot bad reasoning. All right. Finally, they're bounded knowledge. I mean, obviously, don't ask them current information, because you know these models are going to have a knowledge cutoff. They're going to have context window constraints. If you have like a huge source code source base, or if you have a huge source code base, or if you have like thousands of PDFs, you might have to learn the skill of managing that context properly to use these models well. And this is something that's being solved right now, folks, I think. So this is maintaining coherence across extensive reasoning chains is essentially this. There's a lot of arguments, folks, for why these models are not really thinking, right? There's a really cool paper, Limitations on Compositionality. Oh, wait. It's called Limits on Transformers on Compositionality. And this is a really cool paper. I think it's out of Allen Institute and ta-da-da-da. And they argue that these models are not really thinking. They're approximating some heuristics for problems that's not really, compositional, abstract thinking. And they show that by showing that when you scale in the complexity of the problem, the approaches they start to take after complexity level X is quite weird. So that's the argument of that's not a very good depiction of the paper, but check out this paper. My point is just that because they have these limitations on the actual reasoning they do, don't trust that they're actually reasoning like we're reasoning. They do something that looks like reasoning, so we can evaluate as reasoning beings what they're doing and apply our thinking to see if they're coherent and so on and so forth. But don't trust it. Have evaluation pipelines and have procedures to spot inconsistencies and hallucinations and so on, because that can happen at the reasoning chain level. And this is a very frustrating one, but because they don't reason, their ability to transfer knowledge from one domain to another is going to also be limited. So you need to spot that as well. And the sources that I really like for thinking about these limitations are essentially this paper that I just mentioned. There's another one called Reasoning or Reciting, Exploring Capabilities and Limitations of Language Models Through Counterfactual Tasks. And there's this very cool tweet that I liked, which is making the mention that the LLMs in general, they rely on this bag of heuristics to solve problems. So when we're mentioning reasoning LLMs, we're saying, look, this is a model that is closer to how people solve problems, but it's still not real reasoning as we humans reason. So remember that they use these bag of heuristics, and keep your process in check when leveraging their reasoning capabilities to make decisions and so on and so forth. All right. So with that being said, folks, how do we choose between a bunch of options that are out there? Now, I'm going to make a very, I'm going to try to be a little bit quick on the procedure you can implement to make choices between the reasoning LLMs. And essentially what you're going to consider is the very simple heuristic that I would advise you to take is to consider the indexes for how these models are assessed, how their capabilities are assessed. What do I mean? If we go to artificialanalysis.ai, right, we can look at the performance of not all of them, but most of the models that are out there, all right? Both closed source and open source, but not all, because there's way too many models out there and it's complicated. So there's a bunch of tools you can use, like leaderboards or this amazing website by artificialanalysis.ai that I recommend all the time, that they do independent checking of their performance across benchmarks and across different tests that examine different capabilities. So for example, if we look at the Artificial Analysis Intelligence Index, and we see here on the right that this is a combination metric covering multiple dimensions of intelligence, the simplest way to compare how smart models are. Version 2 was released in February 25 and includes MMLU Pro, GPQA Diamond, Humanities Last Exam, Live Code Bench, Scicode, I'm Math 500. See Intelligence Index methodology for further details, including a breakdown of each evaluation and how we run them. So, what does that mean? It means that, okay, these models are the best across these benchmarks. So we can take a look at the methodology index here. And what's really cool is that we can take a look at the evaluation suite summary, and we can look and see what was the evaluation that was used. What does it evaluate? So MMLU Pro is about reasoning and knowledge, how many questions, response type, so it's multiple choice, regex extraction, intelligence index weighting. So this is the weight that this evaluation has on that final index score. So you can see that it's a sixth of the answer. And then you have Humanities Last Exam, which is also reasoning and knowledge. The response type is actually open answer, different from the previous one. And this is really cool because we can actually understand how they're being assessed and what that number reflects in terms of capabilities. So these are models that can spot what's correct in problem-solving tasks. They can actually write down answers for problems that involve reasoning and knowledge across like 3,000 different questions, and in multiple choices, like 12,000 different questions. And then for scientific reasoning, which is like graduate level questions about chemistry, biology, physics, etc., the models did very well on multiple choice. And then for math, they can do open answers in math. They can do numerical answers for I'm. And I mean, for code, you can take a look at, they're very good at generating Python code on different things. So you can see, for example, that because this is Python code, you might think, okay, so this model is going to be better at generating Python code than maybe another language that you're interested in. So that's something you have to consider, like which languages these models speak, and so on and so forth. However, there are a few proxies that we can use to know which model to use. And assume that as API calls, you can use whatever model you want, and you just care about the best reasoning model. And the one thing you're going to have to do is say, look, I need to set up thresholds for what I'm looking for. So, okay, intelligence index. We're going to say that for the intelligence index, we want anything on the top 20, okay? So I could actually go into my little Scally drawing here, and we're going to make a little fancy table. So it's going to be the decision-making chart. It's going to be decision-making chart for reasoning LLMs. Let me make this big so you can see it. 1 second. There you go. So we're going to say, what are the decisions we're going to make here? What are the factors for our decision? So the factors are going to be, we want top 20 intelligence score. So it means that we want a model that's on the top 20, like the top 20 intelligence score models. And then we want the score of that model, okay? So it's like, we're just gonna say intelligence score. That's gonna be a factor, okay? We also want a model that's fast. So this is speed, latency, okay? So how fast it can generate tokens. And then we want a model that's cheap. So we want the lowest cost model. So we're going to put cost right here. So price, cost, etc. What else? You might have specific requirements of your task, which you can put in this little table we're going to create here with your additional requirements. Now, I'm going to draw very horribly because, why not? And this is essentially going to be a little table that we're going to make, and I should make a more decent version of this, but whatever. There you go. And I'm going to just create this. I'm going to put it here. I know it's ugly. There's probably some table library I should download, but whatever. We're going to just make it real quick. And well, obviously we have to have the model. So I'm going to put the model choice here, right? Model. There you go. And again, I'm going to draw up a little thing here. And then I'm going to pull this up here, pull this up here, pull this up here, pull this up here. and then finally put this up here. And now we can select the model we want based on those factors. So I'm going to say, okay, in terms of intelligence score, let's see. We have the highest quality model is O3 Mini. And then we have DeepSeek R1, and then we have KWQ32B, DeepSeek V3. Okay, so we can start putting these model capabilities here. I can actually expand this a little bit, just so we get this information a little bit. Actually, even to be a little bit more, to be even fancier and make this a little bit faster, check out what I'm going to do. I'm going to take the image of these three factors, and I'm going to go over to Claude. I'm going to show the image. So I'm going to open up Claude here. I'm going to show the image. So I'm going to say this image contains three charts showcasing capabilities of different models. Put all the top 5 models across these three charts in the same table with the structure from this image. And I'm going to show like that little horrible table that I was making. So let me just open this up like this. There you go. And I'm going to like copy this image right here. All right. There you go. Because this is a little bit faster than me doing it manually. So let's see what we get. And then we can cross-check, obviously. But let's just first consider these factors. And I guess using Claude is a little bit nicer. There we go. Beautiful. Okay. So folks, I'm going to copy this as an image, put it right side by side with our little chart over there. There we go. I'm going to make this a little bit smaller now. I'm going to pull this up. And there we go. Okay, so we have O3 Mini with a 66 intelligence score. That's pretty good. And then speed latency in tokens per second. We don't have that info. And it's probably because the model is not even present in the top 10 or top however many that were in this chart. So that means that O3 Mini for me is done. I'm not going to use the O3 Mini because it's going to be way too slow. Let's say, right? So then that would go into DeepSeek. And DeepSeek has a intelligence score of 60. The speed factor of DeepSeek was not obtained, which I think is a bit odd because DeepSeek R1 is right here at 24 output tokens per second. But maybe that was just a mistake from Claude. But DeepSeek is going to be the first one that I'm going to put. DeepSeek R1. DeepSeek R1 is a good option. It has a 60 intelligence score. And in terms of speed, I know it's 24 output tokens per second. So it seems to be like a top model. And in terms of cost, it's, let's see how much does it cost. So if I take a look at this cost, DeepSeek AI, again, the cost did not show up on Claude's extraction. I don't know why. Let's see if it shows up here. So here, Gemini, Qwen, Llama, DeepSeek V3, DeepSeek R1 is like $1 per 1 million tokens. I guess we're assuming that we're going to use like the actual DeepSeek R1 cloud, but that's fine. $1 looks pretty good to me. All right. Okay. So we have a first one. And now we can do that for all of the others. And we can go on and take a look at all those factors. So Gemini 1.5 Pro is 49 intelligence score, 254, 0.2. So I can copy those. I can copy those numbers and put them right here. So it's 45, 49 actually, 254. So 254, 254, and Gemini $0.2 per cost token. Let's just make sure we check in across this thing. Yeah, the price for Gemini, yeah, 0.2. That's interesting. DeepSeek R1 is more expensive than Gemini 2.0. That sounds weird, but okay. That's what it was saying there. So we're going to just trust it, 0.2. Folks, and this is Gemini, right? So I can put Gemini, this is Gemini 2.0 Flash. So Gemini 2.0 Flash. And folks, I would continue doing this until I have all the options that I would consider across these elements, right? And I would add on to this table the task requirements right here. So I would put all my task requirements in this little extra bit so that I add more axes on these factors, okay? So let me just show you what I mean. So if I pull this up, right? So in these axis factors, I would put things like, imagine, so let me just put this up. Let me just make this a little bit bigger. Yeah, and here I would put things like performance on task that I could have evaluated myself individually, or my vibe check. Performance on task, my vibe check through the interface, where I give it a score from like 0 to 5 on which model I prefer by vibe checking it and conversing with it, and whatever other quantifiable metrics for how good the model is and how it aligns with my goals. So quantifiable metrics, how it aligns with my objectives, goals, etc. All right. So once we've done that and we have that, what we're going to do is we're going to use a very fun decision-making matrix tool that I took from this very cool website called untools.something. I think untools.co. There you go. Tools for better thinking. And they have one here for decision that I really like, which is very simple. All you have to do is write down the decision you need to make, list the options you have, identify the factors. We already did this part. Score the options on each factor, add weights to the factors, calculate the option scores, pick your winner. Now, and they even give you like a little table you can use here. So I'm gonna just copy this. I'm gonna go over to Claude. I'm gonna say, generate a template table for me following this website's decision-making matrix. And I'll put that as a markdown, okay? So I'm going to give that, I'm going to send that so I can use that table as the decision-making matrix and so on. I can probably just put the factors in there, but whatever. There you go. So what we're doing, I mean, I probably can generate that on top of that thing, but it doesn't matter. So if I go back here, folks, and I go over here, so now what I would do is I already have the factors, right? Intelligence, speed, cost, right? I have the options, DeepSeek, Gemini, etc. option, right? Now to calculate the score, so I'm gonna delete this image from here. To calculate the score, all I have to do is I have to add a factor element on each of those. I have to add a weight to each of these factors, right? So imagine that the weight that I'm going to add to each is, for example, intelligence for me is important, but maybe for my task, I don't need it that much. So I'm going to say that intelligence is a factor of, let's say, 0. It's out of my 100% of the task is 0.2, okay? So I'm going to say here, factor for intelligence is 0.2. Let me make this a little bit bigger. And I'm going to change the color, not to red. It's going to be like orange. So the color of the intelligence score is 0.2. That's the weight of the factor intelligence score. And speed, it really matters to me. So I'm going to give it a 0.4. And then cost also really matters to me. So I'm going to give it also a 0.4. So let's say that speed and cost have similar factors. So now that I have these weights for all of these factors, what we can do is pretty cool. We can create a score based on these factors. So for example, I'm going to create a little extra column on my table here called score. And what this is going to do is essentially, let me just make this black. And what this is going to do essentially is I'm going to, and let me extend this to here. And I know, folks, I am very bad at drawing these things, but stick with me. So we're going to create a little score thing here. And let me just get this like away from our, I guess we don't need this, right? There you go. So now it's going to be, okay, what is the score of DeepSeek R1? Well, pretty easy. I'm going to copy the score here. I'm going to put it here. 0.2. I'm going to put like a multiply. There you go. And then 0.4 multiply. And then 0.4 multiply. And yeah, we can normalize it because this is like $1.24. These numbers here, they're not in the same scale, right? So we have to normalize them to be in a range where we can make a decision. And that can be done in many different ways. But the point is, yeah, we have to normalize these numbers. So 60, it can't be 60 because then it's going to make it look like it's just because the number is 60 is going to make this number too big. So we have to put all of the numbers within the same range so that 60 represents the same thing in terms of each of the factors. But the point is, and the way that I would do that, honestly, folks, I'm not really 100% sure the best way to normalize all these numbers. I guess I would say if I looked at all the numbers in terms of like all of the options that I have, I probably would create some sort of normalization rule based on all the options that I have. But I'm not really 100% sure what would be the best way because I was thinking about that now and I'm not really sure. But I would at least use this as a framework to consider in general which elements to kind of put in the same box. So I would then multiply by 0.2, 0.4, 0.4 by not by 60, but by some function, let's say f of x, f of 60, where f of x is some normalization function. I guess put it into like a range of 0, put it into like a range of 0 to 1, and then calculate the final score like that, and that would give me the decision of the model that I would pick. Obviously, we could go on and experiment, and this can be implemented as like a very nice Jupyter Notebook experiment. Thanks for watching. Don't forget to like and subscribe, and see you next time. Cheers.